So today we're going to be talking about symmetry, specifically two kinds of symmetry, line symmetry, and then we'll later look at rotational symmetry. Okay? So the way we're going to define the word symmetry, you might already have kind of an understanding about what it is. We're going to define symmetry using the idea of rigid motion. Okay? So again, we know rigid motion means that, it's a transformation that results in the shape not getting bigger or smaller, and it doesn't change, side lengths, or it doesn't change angle measures or anything like that. So a figure has symmetry if a rigid motion exists that maps the figure onto itself. All right? So for example here, if you look at this little crescent moon shape, right? If we drew a line of reflection through the very middle of that shape, if we reflected the shape over that line of reflection, it would map right onto itself. It would, reflect right back onto itself so that it would not, even change position at all. Okay? A figure has line symmetry, or sometimes called reflectional symmetry, if a reflection maps the figure onto itself. Okay? Each of these lines of reflection is called a line of symmetry. All right, so we can kind of see that here. All right, I'm not going to have us actually trace this out. I think you guys can just kind of see that, oh yeah, if we were to flip, if we were to trace this on our patty paper or our tracing paper there and, fold it in half, sure enough, the thing would line up. Okay, and so we would have one fold line, you can see right there, that kind of goes down through our triangle. Okay, so looking at this triangle, we have this one fold line right here. Are there any other ways that we could fold this triangle so that it would map onto itself?
No.
Okay, so no. Alex, do you think there's another fold line there?
Oh, no.
No? Okay, so Alex, then if there's no other fold line, the figure has blank lines of symmetry. Well, blank line of symmetry, so it's one. I think the sentence kind of gives away how many is supposed to be there, right? It just says line, so the only number that can fit in there is one. Okay, so the figure has one line of symmetry, and that's it. All right, so let's turn the page here. All right, and just take a few moments here, take 30 seconds, and look at these three figures, all right, and try and draw in some lines of symmetry. All right, so see where you could fold that shape so it would fold right onto itself. Okay, some are more obvious than others, so I will say this: each one of these has at least one.
No.
Each one of these has at least one line of symmetry. Yes. Okay? So see if you can figure it out. All right? You might have to be a little bit creative, but each one has at least one line of symmetry. Okay? So go ahead, take 30 seconds there and look. Absolutely. Absolutely, yes. You can draw a line of symmetry any way you want as long as it's a line. So each one of these has at least one, though. I know, you look at it, you're like, no way. But they're like, oh, wait a minute. Yeah, it's kind of funny, isn't it? That's why it's you think, oh, symmetry, I've been doing this since elementary school. But then you can throw some weird shapes at people okay, I don't know now. It's deceptively tricky, I want to say. Or deceptively easy, maybe. All right. All right. Time's up. Let's listen up here. Jason, does this shape here have any lines of symmetry? Yes. Okay, can you describe a line of symmetry for this shape?
All right, so you can hold it where the two lines.
The single tick mark right here?
Yeah.
It's like a single vertical line right through the center, right there. Okay, any other ones, Jason, for that shape?
Where the two tick lines are.
Okay, so kind of through the middle, a horizontal line through the middle.
No.
Diagonal here.
What? Yeah.
Well, let's see. I'm going to actually take a paper and let's fold it. Let's see. Okay, so let's see. Let's see if it works. Okay, so I'm going to take my rectangle here. It is a rectangle, you're right. Let's take a look. All right, I'll use a straight edge too. I don't want to freehand this too much here. Edge. All right. You said 3 lines of symmetry?
Yeah, because if you did cut it, it just be like a triangle.
Okay, so there's my rectangle, right? We're all in agreement that that's Yeah, my rectangle, okay. I traced it, okay. All right, so now, so how should I try and match this up? Should I try and match this to this?
Yeah.
All right, so I'm going to fold it so that those two corners try and line up. All right, you can kind of see the problem here, right? It's not... Now, I could try and fold along the diagonal here, right? If I fold along the diagonal, that could work, but you can kind of see... See, it does not match up diagonally. Does not match up. Okay, now, listen up. Listen up. What kind of quadrilateral would fold that way? A square, a square. A square would fold that way. Rectangles do not. Okay, one second. Let me just get this down. So we have two lines of symmetry. Okay, question. Right. Okay, yes. That is exactly right. It is the same areas, and in fact, it's the same shape, but it's not the same shape over a reflection. You have to like kind of rotate it some, right? This, Kwanye, if I fold it along this vertical line, it's the same through a line of reflection, right? Like if I just reflect that side over, they're the same. Or if I reflect the top down, then they're the same. But if I reflect across this diagonal, it is not the same. It will be the same shape, the same size, and the same shape, but the reflection doesn't make it match up. It would be like a rotation maybe or something like that. Okay? A square would give you those diagonals, yes. Okay? Great. So excellent work there. All right, let's go to Curtis. Curtis, how many lines of reflection were you able to come up with for this triangle right here? Just one, yeah. Okay, and where is it? Yeah, not too sure where. So there is one here, and let me show you. Eli, you want to describe it?
Yeah.
Okay.
So if you turn the paper so the straight line at the bottom is straight.
Yes, let's see here. So if I rotate my paper, because I don't have a whole lot of room on my desk here, let's see if I can get that to fit. And got too much going on over here. All right, something like that, maybe. Sorry, it's not. Okay, there we go. Something like that? Okay, so you folks see that even though the shape is turned here, we have this base and then these two sides. And so, yeah, if we go right down the middle there, okay? One line reflection. This triangle is almost the same triangle as what? The one on the previous page. If you look at the previous page, it's almost the same triangle, it's just turned. Okay, so there it is. There's the one line of symmetry, right there. Okay, pretty crazy, right? So it's like, you can see how these get a little bit trickier when you start like turning shapes and things, right? So we got to be careful there. It's not as easy as you might expect. I mean, it's not terribly hard, but it's still, you can still get tricked up some, mixed up something. Okay, very good. Let's go to, all right, so Colin S. Colin S. How many lines of symmetry did you find for this kind of L-looking thing here, Colin? You were able to come up with one? Okay, that's fine. There is one. All right, hang on. Let me see. Tristan, were you able to come up with a line of symmetry for this shape? Did you draw anything? I can take a look, too. Okay, not yet? Okay, that's fine. It is kind of tricky to see this one. Courtney, how about you tell me? Where is it, Courtney?
You would take, if it's like this, you would take it, hold it on top of each other.
So, yeah, if we go right through like that, it will match up. There's one line of symmetry there, and it's right where those two things fold. And again, if you don't believe me, I can show you here real quick. You believe me? No, who doesn't believe me? All right, Kwanye does not believe me. All right, well, Kwanye, I'm gonna show you here. Not because I like proving you wrong, but just to, you know, gain your trust here. All right, so again, Kwanye, I hope I'm doing a good enough job tracing, right? You're okay with my tracing so far? It's perfect. Wow. Shoo, thank you. That makes me feel really good. Okay, so there's our shape, right? Now, I said my line of symmetry is right here, so I'm going to endeavor to try and fold it well here. So let's see. Okay, it's kind of hard to get it matched up exactly, but It's pretty close, right? It's pretty close to being matching up there, and then there it is. Okay, so it does work. How about that? Okay, how about that? Now, of course, there are other ways to cut it so that the areas are equal, right? So, like, I feel like, you know, Quania's kind of argument earlier was like, but Mr. Witt, if I took that diagonal, that would cut the shape into 2 equal parts, and she's right, right? There are other ways to cut this into 2 equal parts too, but the key here is, does it reflect onto itself? That's what we want to really ask, okay? Okay, so we're going to skip question 1 here, but I really like question 2. What figure or what kind of shape would have an infinite number of lines of symmetry? Debbie? A square? So squares, no. Squares have a limited number. A line? You know, a line you might be able to get away with that because it goes infinitely in either direction, so any place you put that could be one. So a line. Okay, but yeah, Quania, a circle, exactly right. So a line, I'm going to put in parentheses, but a circle for sure. A circle for sure. But I really think a line would work there, Alex. That's true. That's a new one for me. Yeah.
For that third one, wouldn't you be able to actually fold it over, like the other one?
Fold what? This way up, you mean?
No, if you were to take that corner and move it over to the right corner, so it was your
I don't. I'll have you show me later on. I'll have you show me later, okay? All right, folks, we're not quite done yet. Let's keep going. Oh, okay, number 3, I guess, is kind of good. We don't have to write anything down for number 3, but a figure undergoes a rigid transformation, rigid motion, such as a rotation. If the original figure has line symmetry, will the image of that figure also have line symmetry? So again, let me ask the question. If a figure has line symmetry, so if like the original or pre-image has line symmetry, and then we like reflect or rotate or translate that, will its image also have line symmetry? Yeah. The shape doesn't change, right? So it should have line symmetry. Okay. Anyway, let's go down here. The second type of symmetry we want to be familiar with is rotational symmetry. Rotational symmetry. Okay. So a figure has rotational symmetry if a rotation maps the figure onto itself. So line symmetry, if a reflection maps a figure onto itself, that's line symmetry. Rotational symmetry, if a rotation maps a figure onto itself. Okay? One key thing here, so in line symmetry, we need to be able to come up with the number of lines of symmetry. In rotational symmetry, one thing we're going to need is to be able to come up with the angle of rotational symmetry. Okay? The angle is the degree measure that's greater than 0, but less than or equal to 180 that rotates the figure onto itself. Okay, so here's the key to figure out that angle of rotational symmetry. If you look over here, the star here has an angle of rotational symmetry of 72 degrees. That means you only need to turn it 72 degrees, either clockwise or counterclockwise, to get it to map onto itself. How does anyone think? How do they figure out that 72 degrees was the measure there, besides just using a protractor? What can we do, Alex? Not sure? Okay. Let me give you a little bit of help, okay? To rotate the star completely all the way around would be what number of degrees? 360, right? But we can see that we don't need to rotate the star 360 degrees for it to get it to match up to itself, right? We only need to rotate it this much, right, to get it to match up to itself. So how many times can we do that? Well, 1, 2, 3, 4, and then 5 will get us back to the beginning. So if it takes 360 degrees to go the whole way around, but we can match up to itself 1, 2, 3, 4, 5 times, how can I figure out what an individual turn like that would be? Divide. What's 360 divided by 5? 72. 72. So there's the angle of rotation, okay? So an angle of rotational symmetry is a fractional part of 360 degrees. Notice that every time the 5-pointed star rotates, 360 over 5 equals 72 degrees, the star coincides or matches with itself. So the angles of rotation for the star are 72 degrees, then plus another 72 would be 144, plus another 72 is 216, plus another 72 is 288, plus another 72 would be then 360, okay? So if a copy of the figure rotates to exactly match the original, the figure has rotational symmetry. So let's look here at our triangle. Okay, now it says to use tracing paper here, but I don't think we need to do that, okay? This triangle, okay, has some line symmetry in it, but let's focus on the rotational symmetry right now. So how many times would I need to rotate this triangle till I get back to the beginning? 3 times, right? I would rotate this point up to here, and then I would rotate down to here, and then I would rotate back to the original. So 3 times, okay? So 360 then, that degree, we're going to divide that by what? By 3, the number of times it took to go around, right? 1, 2, 3, back to the original. So 360 divided by 3 is 120 degrees. So by how many degrees do we rotate the figure? It's going to be 120 degrees. Okay? Divided by however many times you can like kind of rotate it, okay? What are all the angles of rotation? Well, the first angle of rotation is 120 degrees, but then we can add 120 to that, 240, so we can also rotate the triangle 240 degrees, and we can add 120 to that, and it'll be 360 degrees, which is then back to the original. Okay, back to the original. So there's all the angles of rotation. All right? All right, so let's look at the next shapes here. All right, so for these next shapes, what I would like you to do is determine whether each figure has rotational symmetry. Okay? And I'll give you a hint here. Some figures do not have rotational symmetry. Okay? If so, identify all the angles of rotation less than 360 degrees. So look at these 3 shapes and identify what their angles of rotation are going to be. All right? So for example here, for the star, the angle of rotational symmetry was 72 because it took us 5 times to go around, so 360 divided by 5. Here the triangle, it took us 3 times to go around, so it's 360 divided by 3. Now look at these shapes and tell me what their rotational symmetry would be if they have it. Okay, so go ahead and do that real quick. I'll kind of come around and help. This one's a little bit trickier. So yeah. Yeah. I'll get you Mitch. I'll get you Mitch in a second. You could, but it wouldn't match up. If you hold it that way, again, like you're saying, this is your fold line right here. Those can kind of come. I'll show you here. It won't come over. That's right. Use pencil there, Tristan. Okay. 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 What's that? Measure.
If it's only like 360,
correct, because every shape has 360 degrees. It's kind of trivial. Good, that's exactly right. Yes, good, exactly right. Okay, so you're not sure about it?
you're going to rotate it and not go back.
Yes.
There's no lines.
Okay, here's rotational symmetry here. So count how many times you can turn it before it gets back to the original. How many turns does that? Yep. So, right, so every shape, square is 60, so it's matches to itself. So it's trivial to say. So we say no.
Square has 360.
Yeah, you're right.
All right, now you're right. You can bring that in.
So this one, wait, did you tell me this?
Exactly. This triangle, it did match up perfectly. This triangle matches perfectly. No. So that's trivial. So 90. How many times can you turn that thing 4 times? Right, we flip it. Oh, yeah, not the line symmetry here. Not the line. So you're right with the line. That's good.
So that way they can't hit 2 here. Or they can hit here, they can hit 2.
That's right. So this is line. This this number here. What is this number? Okay. No, those are right. That's correct for line symmetries, but I'm asking for rotational symmetry. So what I mean is, how many times could you turn it so that it matches onto itself? Well, for example, I could rotate this point up to here, and then that point to there, and that point to there, and then back. So it'd be 1, 2, 3, 4. Well, you want to take 360 and divide that by 4. So 360 goes the whole way around. Divide by 4 to get an individual angle measure. Okay, do you have a calculator for that or something? Okay, you can do it. Okay, 360 divided by 4. Okay, that's right, but it shouldn't be 240. 360 divided by 4 is not 240, it should be 90. You can't just turn it to there, you have to turn the whole shape. Now this one, there are three, but if I turn this one to this one, it's not the same shape as it is right now. Okay. So, folks, this is a little bit trickier to see, right? I noticed I was walking around there, some people had some difficulty, and that's okay. This is a little bit harder to see, okay? Because it's harder to imagine rotating a shape than it is like folding it. I feel like we're much more, used to folding things. Anyway, let me give you a little trick here to maybe help you. All right, if you take your shape here, for example, and you make a little mark on one of the vertices. Let's just mark like this vertex right there, okay? Oh, thank you, sir. All right. I'm going to do the same thing here on my patty paper. I'm going to just kind of like trace my shape. Oh, sorry. Thank you. Okay, so again, what I did is I drew a point on one of the vertices of my shape, and then I'm going to do the same. I'm going to trace that shape, putting the same point that I had on the shape there. Okay, so there it is. Now I'm going to take this shape and I'm going to rotate it. I'm going to keep turning it until it matches back up. Okay, so there's 1, right? I'm going to keep turning, keep turning. 2, keep turning. 3, keep turning. 4. It takes 4 times for that point to travel around my shape, so 360 divided by 4, 90 degrees. There's the answer. Okay, if I do the same thing for the triangle here, same thing for the triangle, watch what happens. And some of you guys are able to see it without even having to trace it, that's fine. I'll put a point right here just because, put a same point there. And now I'm going to try and turn my triangle until I can match it back up here, and you can see that it's not quite matching. Okay, kind of like matches there, but it's still not on top of itself until I go the whole way around. So what's the angle of rotation here? 360. But is there any shape that doesn't have 360-degree rotational symmetry? The answer is no, right? Every shape has 360-degree rotational symmetry. So that's trivial, and so we just say there's no rotational symmetry. Okay? We're only interested if it turns less than 360 degrees. So there's no rotational symmetry there. Now what about this arrow? What's its rotation symmetry? Yeah, there's 2 turns or 180 degrees. And again, if you don't believe me, all right, watch this. Again, I'll put a arrow right there, and a point on the top of the arrow there. I'll kind of re-sketch it. Try to be accurate, but Okay. And you gotta rotate it, turn, 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 turn. So there's 1. Turn, 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 turn. There's 2. So 360 divided by 2, 180 degrees. Okay, so what figure is mapped onto itself by a rotation of any angle? A circle. Another circle. Okay? Circles. All right, let's scoot down here and describe these symmetries. So let's look at this shape right here. It says, describe the symmetry of each figure, draw the lines of symmetry, name the angle of rotation, or both if the figure has both. Okay? So does this shape have line symmetry? Yes, it does. So let's see here. Let's go to... So Addie, can you give me one of the lines of symmetry for this shape here? Okay, down the middle, so like a vertical line?
Yeah.
Okay. Are there any other lines of symmetry here? Okay, yeah, we got a horizontal one. Addie, or do we have any more? Melissa? Yes, actually we do have 2 diagonal ones as well. They will fold to match up. And again, if you're not sure, feel free to use your tracing paper to convince yourself that you're right. So now, are there any other lines of symmetry?
Yes.
There are. Alex, where?
Well, you know, you actually could divide them up.
Okay, so we got 1, 2, 3, 4. How many lines of symmetry do we have here?
4.
Just 4, right? This first one I counted right there. There's 2, 3, and 4. Okay, so there's 4 lines of symmetry. Be careful how you count these. Don't double count them because, you know, you count the one here and you're like, oh, that's 5. No, it's not. It's still the same first one that you counted. 2, 3, and 4. So 4 lines of symmetry. Okay, good. And then let's go to column W. How many times can we turn this shape, Colin, before it goes back to its original position? And this might be a little bit harder to see. I'll trace it for you here real quick. Let's see. Okay, so I'll trace. So again, I'll put a point here on the top. It doesn't matter where you put your point, just somewhere there. Let me retrace it here real quick. No, if you can count it up and you feel confident in your counting, then do that. Okay, but if you're not confident, that's fine. We'll just. So let's count here, right? So we'll rotate, turn, 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 turn. Right there. That's 1, right? 2, 3, and then 4 back around. So there's 4 turns, which means we do 360 divided by 4, which is 90. Okay, very good. Thank you, Colin. 90-degree rotational symmetry. Okay, which means you could rotate this figure 90 degrees. We could rotate it 180 degrees, which is 90 plus 90. We could rotate it 270 degrees, because that's 90 plus 90 plus 90. Or we could rotate it, of course, 360 degrees, because that's 90 plus 90 plus 90 plus 90. So you can just keep adding 90 to your rotations, and that'll give you the shape again. So there it is. Okay? Good. All right, let's look at one more, and then I'm going to give you guys your assignment here. All right, letter B. All right, let's go to Zach. I know you just got in here a little bit late, Zach, but I think you can still help us out here. So, can you see any lines of symmetry here? That means we could fold it onto itself. In the middle, okay, like a vertical one, like this. Okay. Shh. Anything else? Okay, kind of like this way. Okay. Anything else? Yeah, the opposite direction there. Very good. Okay, is that all? Yes. So again, 1, 2, 3 of them. 3 of them. So 3 lines of symmetry.
Wait, so why does it say 4?
Where does it say 4? Oh, 4, sorry, 4 is for, that's for the shape above it. That's all. Okay? And then rotational symmetry. All right, how many times could we turn this? Let's go to Eric. Eric, how many times could we turn this before it goes back to itself? 3 times. So it's 360 divided by 3, 120 degree rotational symmetry, which means we could turn it 120 degrees, we could turn it 120 plus 120, 240 degrees, or we could also turn it 360 then too, of course. Okay? But every shape can be turned 360. All right, great. So let me give you guys your assignment then. Okay, you have about 15 minutes to work on it here. Okay? So your assignment starts on page 106. Yes, 106. Say again, sorry? 120 degrees. 120 degrees. It's 360 bucks. All right, page 106 to 107, numbers. All right, let's see here. One through 8 and 12 through 16. Okay? So go ahead and get started on that. 1 through 8, 12 through 16. Gentlemen. No, I'm looking back here. Let's get to work, please, guys. Okay?
The ones on the bottom.
Yes. You may skip the ones on the